Hello everyone. Thank you for attending the BAS Electrochemical Webinar 2023 Winter. I'm Miho from International Sales Team and I will be the moderator. Today, it will be the fourth lecture of a series of lectures in the field of coordination chemistry and electrochemistry, introducing basic electrochemical methods and applications with a focus on organic complexes, introduced by Professor Masa-aki Haga from Chuo University. Today's theme is coordination chemistry and electrochemistry, cyclic voltammetry and reaction mechanism at Electrode Part 3.
Good afternoon. This is Masa-aki Haga of these lectures. This is the fourth lectures on cyclic voltammetry and electrochemical reaction mechanism at the electrode. Continuing on the previous three lectures, today I deal with proton-coupled electron transfer mechanism. Then I will introduce you new steady-state voltammetry technique, which is rotating disk electrode. In the previous three lectures, I have talked some of the electrode reaction mechanisms and their features of cyclic voltammograms, starting from EC mechanism and EC-EC and catalytic reactions. Today, I focus on the proton-coupled electron transfer reactions, which is often seen in aqueous solution in the field of not only organic and biological systems, but also in organic chemistry. In aqueous solution, there are two different descriptions. First case is one is that electrode process of A by AH couple is fully reversible, which is written by these chemical equations involving both electrons and protons. The another case too is the A is reduced by the electron transfer, followed by proton transfer. In this case, the electron transfer process is the rate limiting step, and all the protonations are at equilibrium, which is expressed by the square scheme. The first example for the proton-coupled electron transfer is the ruthenium-aqua complex, which acts as the water oxidation catalyst. The ruthenium-2-aqua complex is converted to ruthenium-3 hydroxy and then ruthenium-4-oxo complex by proton-coupled oxidations. The deprotonation avoids charge buildup on the ruthenium centers, which makes further redox step difficult. In square wave voltammogram as shown here, the two waves observed at the pH 2.5 and the first peak at 1.2 volt is shifted to the negative potential directions. By plotting the oxidation peak against the pH, the Pourbaix diagram in the left-hand side was obtained. The high oxidation state of ruthenium is stabilized by the proton-coupled oxidations and easy access by lower potentials. The second example is the electrochemical oxidation of phenol. As you can see, irreversible waves, oxidation waves observed at 1.15 in Britton-Robinson buffer at pH 3. When the solution pH is increased, peak is shifted towards the negative potentials directions. In this case, proton transfer occurred simultaneously with after the electron transfer, and then the following chemical reaction occurred in which the phenoxy radical is dimerized. By analyzing CV carefully, the successive chemical reaction rate was determined, and the concerted electron-proton transfer process was found in these systems. In a square scheme, four species are interconnected by the electron transfer and proton transfer, and each equilibrium are represented by the respective oxidation potentials E1 and E2, and the acid dissociation constant Ka1 and Ka2, which can be obtained from Pourbaix diagrams. Pourbaix diagram is constructed by plotting the oxidation potentials as a function of pH. In this figure, at the lower pH regions, the potential does not change with increasing pH, and then further pH increase, the potential moves to the negative potential linearly. The inflection point here corresponds to pKa2. At more higher pH regions, peak potential does not change again with increasing the pH. The inflection point corresponds to pKa1. Therefore, Pourbaix diagram provides the important information for thermodynamic parameters about the redox-active species. The slope of the line obtained in the Pourbaix diagrams depends on the number of electrons and protons in proton-coupled electron transfer reactions. When the line slope for the potentials versus pH plot is 0, 1 electron only involved, and 58 millivolt. In this case, 1 electron and 1 proton are involved in the reaction. Here's the list of the slope value, which provide us the number of protons and electrons involved. From now on, I would like to introduce our work related to proton-coupled electron transfer in ruthenium compound to help you better understanding about the proton-coupled electron transfer. Here shows ruthenium bis dipyridine containing 2-pyridyl benzimidazole complex, which exhibit the square scheme involving electron transfer and proton transfer. At ruthenium-2 oxidation state, the pK for proton dissociation occurred at 6.62, but once oxidized to ruthenium-3 state, the pK became 0.90 volt, which is dramatically lowered and more acidic. The ruthenium-2,3 oxidation potential is shifted from 0.86 volt to 0.41 volt after the deprotonation. Here is a cyclic protonogram of another ruthenium complex as shown here. When the solution pH was changed from pH 2.8 to 10.3, CV waves to move to the negative potential directions. From the CV measurement at different pH, Pourbaix diagram was obtained, and pK value was calculated by analyzing potential pH plot. by using Nernst equations. At pH 5, the complex is oxidized to ruthenium-3 state. The slope is 120 mV, indicating 1 electron, 2 proton reaction occurred at this pH. On the other hand, at pH 7, the slope becoming 60 mV, which indicate 1 electron, 1 proton reaction occurred at this pH. Here shows two ruthenium complex, complex 1 and complex 2. Both complexes are quite similar, only difference is that ruthenium complex 2 contain a ruthenium cyclometallic bond. As shown here, only the nitrogen atom of complex 1 is replaced by the carbon atoms. Both potential pH plot is shown here. The complex 2 is blue line and complex 1 is red line. The line of complex 2 is shifted to the negative potential side at entire pH regions, and the inflection point is moved to the higher pH region in complex 2. The pK value of both complexes for different ruthenium oxidation state are summarized in this table. The initial pK1 of complex 2 in the ruthenium-2 state is 10.94. When oxidized to ruthenium-3, pK becomes 6.46, and lowering the pK value indicate at ruthenium-3 state, complex is more acidic. We can apply these two complexes to redox storage or redox flow batteries. Two electrode systems separate Nafion membrane was constructed containing acetonitrate 0.1 molar sodium chloride solutions as the solvent in the unbuffered condition. Complex 1 was used as the active material at the cathodic side, and complex 2 in the anodic side, and galvanostatic charging-discharging experiment was performed at a constant current of 0.1 mA. The charging-discharging behavior of both cells accompanied pH change are monitored and shown in these top figures. The red line shows the voltage change during the charging and discharging, and the blue line shows the pH change. When charging, the cathodic cell changed to acidic and the anodic cell to basic, and when discharged, both return to the neutral. From Pourbaix diagram starting at pH 7, both cells undergoes the 1 electron 1 proton reactions, and complex 1 oxidized, and another side complex 2 is reduced. As a result, the potential's voltage is accumulated and the proton gradient generated at both cells. This is how the energy storage occurred on the redox flow batteries. By the way, it is well known the biological membrane proton gradient inside and outside the membrane are essential for ATP synthesis, which is important for energy productions. Therefore, in our systems, the pKa difference stored as the potential voltage change, and this is quite similar as the biological energy storage systems. Recently, several energy storage devices based on proton-coupled electron transfer reaction in aqueous solution have been reported. Here shows two examples. First one is iron triimidazole coordinate complex. A single ion compound shows proton-coupled electron transfer at the wide range of pH, and they used Electrode batteries at basic and acidic potential using basic and acidic potential difference. Second example is the pyrene tetron, which is similar to the quinone structures, which shows proton-coupled electron transfer and used as the anodic side, and combination of manganese dioxide reductions used as the cathode. These reactions take place in water and significantly stable for repeated cycle. I would like to summarize first part. First, proton-coupled electron transfer is ubiquitous reaction in inorganic materials, organic, organometallic, and biological systems involving CH, NH, etc. bond. Second, the Pourbaix diagram includes a lot of chemical information about the pKa and potential EHAF with different oxidation state of the materials. The materials shown in PCT have potentials to store the energy through pK difference and potential difference. Here's a reference of first part. If you're interested, please read these literatures. Changing the subject, I'm going to talk about rotating disk electrode next. As I told you, the cyclic voltammogram technique is transient, non-steady state method. On the other hand, the rotating disk electrode measurement is a steady state method since the diffusion layer on the electrode remain constant. As I have talked before, mass transport of the analyte to the electrode occurred in three different modes. One is diffusions, migrations, and convections. In some time, we use hydrodynamic electrochemistry, including rotating disk voltammetries. As the electrode rotates, the adjacent solution is pulled along by viscous drag and is thrown away from the axis of rotation by centrifugal force, as shown here. The expelled solution is replaced by flow normal to the electrode surface. The rotating disk thus acts as a pump which moves solution up from the below and then out away from the electrode. As a result, the thickness of diffusion layer keeps constant. Therefore, the steady-state sigmoidal shaped IV curve is obtained. Current is described by Lebesgue equations, and the current is proportional to the square root of the rotating rate. The faster rotation rate, the larger current obtained. By considering the mass transfer at rotating disk electrode condition, the convective-diffusion equation provides the flux of the analyte, which gives the current at the electrode. Flux is composed of two terms. The first term is convection and fluid velocity, and the second term is diffusion. From fixed second law, as the x-axis normal to the electrode's surface is given in these equations, in the steady-state condition, the delta C over delta T is 0. Finally, considering the boundary condition, Levitch equation was obtained. RDE exhibits the sigmoidal shape steady-state Voltammogram by linear sweep voltammetry, and limiting current is described as Levitch equations. Since Voltammogram has a limited current, so we can discriminate oxidation state in solution, either reduced or oxidized species present. As an example, again, ruthenium bis-benzimidazole-pyridine or benzene complex. In the case of nitrogen atom coordinated complex, the line of red colors, RDE voltammograms, gives the anodic current, which means the ruthenium-2 to ruthenium-3 oxidations takes place. On the other hand, the blue line for ruthenium cyclomethylated carbon complex, RDE, gave cathodic current, which means reduction occurred. Therefore, the original ruthenium oxidation state is ruthenium-3 state, and reduced to the ruthenium-2 state. Therefore, the steady-state RDE measurements provide the clear information for the oxidation state of the materials. We have to consider the thickness of diffusion layers under the rotating disk electrode condition. For Levitch equation to hold, we need to perform the experiment within rotating speed between 10 to 1000 Hz. In the case of typical molecules, diffusion coefficient is 9 times to 10 to the minus 6 square centimeters per second, and kinematic, the viscosity is 0.01 square centimeter per second. In this case, the thickness of diffusion layers, the rotating rate is 1000 rpm, the thickness is 15 micrometers. However, when the rotating rate is becoming 10,000 rpm, the thickness becoming thinner and 4.8 micrometers. At first, I show you the movie how the rotation rate affects the potential current curve on RD Voltammetry. When the rotation rate becoming higher, the limiting current becoming increased. For analyzing the RD voltammetry, we should measure the IV curve by changing the several different rotation rate and check the rotation rate dependence by Levitch equation. That is, the current is proportional to the square root of the rotation rate. Please check the linearity, and also the line will be through the origins. In order to know how to analyze RDE voltammograms, one example is pick up again ruthenium bis-benzimidazole-pyridine complex. Here shows RDE voltammograms. and the rotation rate dependence. From the voltammogram, we can read the limiting current value, IL, read the current value on the curves and the potential at that point, read several points on the curve in the same way, substitute the potential E and the current value I in the nearest equations, plotted them. Take the potential on the y-axis and the logarithm of the ratio of the current values on the x-axis, and find the halfway potential E0 from the intercept of the line. Furthermore, plot the limiting current value at varying rotation speed against the square root of the rotation speed to see if it is a straight line through the origins. In the previous analysis of the RD curve, a Leibniz plot at different points of the potentials may result in the curve. In this case, there is a possibility of an EC mechanism in which chemical reactions are occurring in addition to the electron transfer at the electrode. In this case, the chemical reaction rate can be determined from the intercept by plotting the inverse of the limiting current and the square root of the number of rotations. This is called Kotecky-Leibniz plot. An independent ring electrode is introduced by surrounding disk electrode, which called rotating ring disk electrode, and two electrodes can be controlled separately. The ring is effectively downstream to the disk under the rotating conditions, and ring electrode can catch the intermediate or electrolyte species at the disk electrode. In particular, this type of electrode is efficient to detect the intermediate. Once A is oxidized to B at the disk electrode, the reaction mechanism can be elucidated by either reduced generated B at the ring electrode or by increasing the current when the observed B reacts to the become X and is further reduced to Y. So we can catch the ring electrode for the intermediate reduced species. Most famous electrode reaction analysis using the rotating ring disk electrode is the four-electron reduction of dioxygens. In the reduction of the dioxygens, hydrogen peroxide may be formed in the two-electron reduction. So by setting the potential to plus 1.4 volt, which can decompose this hydrogen peroxide, and observing the change in current value, we can clearly see whether the two-electron reduction is taking place. In mononuclear cobalt porphyrin complex, the current value is observed because the reduction of oxygens is taking place at the disk, but the current value of hydrogen peroxide also observed at the same time, indicating this complex works electron reduction product. On the other hand, in dinuclear cobalt porphyrin complex facing each other's, the reduction wave of dioxygen is observed at the disk electrode, but almost no current is observed at the ring electrode. This provides that the four-electron reductions occurred on this complex. Here is a summary of this part. At the rotating disk electrode, forced convective mass transport occurred, and therefore the steady-state voltammogram is obtained. Second, analysis of electron reaction using the rotating disk electrode is very useful for detecting intermediate. Here is a reference of this part. Please read if you're interested. Thank you for listening to these lectures.
Thank you, Professor Haga. If you have any question regarding to the lecture or other topics, you can contact us. In addition, the movies of a variety of topics you can watch here in the BAS channel, which you can follow and have access to the latest news, including the past webinars. The next webinar is already scheduled for April 5th. It will be a continuation of the rotating ring disc electrode applications. Then, the spectro-electrochemical methods will be explained. For today, thank you and have a nice week.